The first paper is network monitoring for wireless sensor network using vertex cover models. The speaker is Mona Abdu
يمنى عادل.
من عدل, Asyut International Technological University.
Yeah.
The other authors are Muhammad Abdul Rahim, RIT Dubai, Amr Abdul Hafiz, Southeast Technological University.
Yeah.
And stage is yours.
Yeah.
10 minutes, please.
Thank you. The table of contents today is introduction, related work, methodology, and comparative analysis and conclusion. The smart technologies and digital transformation, smart systems like homes, industries, transport rely on autonomous operations. Integration of ICT, IOT, and wireless sensor network drives intelligent automations. Wireless sensor networks are the sensing and communication backbone of any IoT ecosystems. The wireless sensor networks consist of sensors and routing nodes distributed to monitor environmental parameters. It's capable of sensing, processing, and transmitting data wirelessly. It's used in smart cities, agriculture, military, disaster management, and more. Of course, we have challenges in the wireless sensor networks. We have critical constraints in wireless sensor network, energy limitations like battery-powered operation, computational power, restricted processing capabilities, communication range, its limited wireless transmission, and memory constraints, small storage capacity. And the monitoring challenges ensure network connectivity, integrity, and operational status. Continuous monitoring becomes infeasible as network scale. Need for optimization strategies, balancing resources consumption for performance. The problem formulation, as we can see on the right side, the wireless sensor network represented as undirected graphs, G of V and E, where V are represented the vertices, sensor nodes, and E refers to the edges, which are the communication links between them. So our objective today is to select the minimal monitoring nodes, ensuring full link coverage. The minimum vertex cover definition is about defining the smallest subset, such that every edge I and j belongs to E is covered by at least one vertex in C. The applications, network monitoring, resource placement, and infrastructure design. The challenges in solving minimum vertex cover, that MVC is MB hard problem, that we have to find the exact solution infeasible for large wireless sensor network. Local search methods risk premature conversions. Large scale dynamic networks need approximate or heuristic approaches. The meta-heuristic solutions, why we use meta-heuristic? Because it handles large and irregular search spaces effectively, provide near optimal solutions in reasonable time, balance exploration versus exploitation, suitable for dynamic wireless sensor environments. So the common meta-heuristics for minimum vertex cover is like differential evolution and particle swarm optimization. So we go with the related work. The minimum vertex cover problem is a key topic in any graph theory and network optimization. In wireless sensor network, minimum vertex cover helps minimize the number of active nodes while maintaining full monitoring coverage. We have classical approaches like branch and bound, branch and reduce, integral linear programming. It ensures optimally but are limited to small or medium-sized networks due to high computation. Approximation algorithms provide near optimal solutions efficiently, often use greedy strategies selecting high-degree vertices first, serve as good initial solutions for meta-heuristics. We also have meta-heuristic approaches which balance global exploration and local exploitation. Its popular methods like genetic algorithm, anti-colony algorithm, simulated annealing. So differential evolution is the key focus of this work. Differential evolution adapts naturally to both continuous and discrete optimization problems. For the minimum vertex cover problem, solutions are represented as binary vectors. Mutation and crossover operations explore new covers. Repair operators ensure every edge remains covered. Enhancement include greedy initialization for faster conversions, adaptive parameters for dynamic balance, hybridization with local search for refinement. In wireless sensor network, differential evolution minimizes energy by selecting efficient monitoring nodes. The minimum vertex cover application in the wireless sensor networks is like energy awareness, nodes vary in reasonable energy, dynamic topologies, adaptation for failure or mobility, trade-offs between energy efficiency, accuracy, and reliability. The research gaps limited standardized benchmarks for wireless sensor-based minimum vertex cover problems, few hybrid approaches integrating DE or reinforcement learning, lack of focus on dynamic, large-scale, and heterogeneous wireless sensor network, minimal exploration of quantum and ML-enhanced optimization. So, let's talk about algorithm. Application of differential evolution for minimum vertex cover DEMVC algorithm. It integrates DE with customized repair, local search, and filtering mechanisms. The method aimed to balance exploration and exploitation for efficient wireless sensor network monitoring. Experimental evaluations are conducted on a standard benchmark dataset. The problem context. The minimum vertex cover problem seeks the smallest set of nodes covering all communication links in a network. In wireless sensor network, solving minimum vertex cover reduces the number of active monitoring nodes, thereby saving energy and extending network lifetime. The problem is MB hard, making exact methods impractical for large networks. Meta-heuristic approaches like DE provide efficient near-optimal solutions. So, our framework in the proposed DMVC follows a core DE structure enhanced for discrete and constrained environment. The key phases include initialization, mutation and crossover, repair, local search, selection, and filtering with the core search. As you can see on the right side, our flowchart for the workflow. First, we initialize a set of feasible solutions. Then, for each generation, we apply mutation and crossover, then repair infeasible covers, apply local search refinement, evaluate fitness, and finally select best individuals for the next generation. Then we apply filtering and core search to maintain diversity. Finally, we return the best vertex cover found. The experimental setup benchmarks from tense Dymax challenges, the Center of Discrete Mathematics and Theoretical Computer Science were used. These include small and large graphs representing diverse wireless sensor network scenarios. As you can see on the right side, our dataset we used in the algorithm. The parameter configurations. The DEMVC performance across networks. Comparison with other algorithms, and performance analysis. Accuracy. The DMVC finds optimal or near optimal solutions for most datasets. Efficient. It was fast conversions with strong local refinement. Scalability. It maintains good performance on large graphs. Hybrid strengths, repair, and local search significantly improve DE performance. Energy efficiency, particularly effective for wireless sensor network scenarios. Conclusion and the future work. The differential evolution, the DMVC algorithm achieved strong results across Dymax benchmarks datasets, matched optimal solution for small-scale graphs, produced near-optimal solutions medium-scale graph, and slightly reduced performance on very large graph. Demonstrated robustness and consistent performance across multiple runs. It was strong diversity maintenance, stable convergence. The DE excels in mid-sized graph. It outperforms greedy baseline and are competitive with traditional meta-heuristics, achieve solutions close to the optimal with low deviations. The key contributions. Developed DMVC framework with binary encoding, repair, and local refinement, conducted comprehensive benchmarking on standard and real-world datasets, provided comparative analysis revealing complementary strengths of DE, proposed a unified conceptual model linking both evolutionary methodologies. Final remarks: the DE proved to be powerful optimization tools for the minimum vertex cover problem. Its success in wireless sensor network monitoring establishes a foundation for hybrid and adaptive methods. Future work will focus on extending these approaches to dynamic large scale and real world network environments. Thank you. Any questions?
Thank you. Any questions? Thank you very much.
Thank you. Thank you.
The second paper, scheduling model for IoT in hybrid fog cloud computing. Authors Mahmoud Hamid, Military Technical College, Egyptian Armed Forces, Mohammed Ghitas, Jalala University. We have only 2 minutes, 10 minutes.
Good morning, everyone. My name is Mohammed Ghitas from Jalal University, and today I will give a presentation about our papers with title Scheduling Model for IoT in Hybrid Fog Cloud Computing. Starting with abstraction and modification. As we know, IoT applications face a lot of problems, and the main problems is the service delay. IoT applications generate huge and variety of data, and the data has to be moved to cloud computing for processing. But the transmission of data to cloud computing incur a service delay, which is critical for real applications. So, fog computing introduced as intermediate layer to reduce the service delay by processing and bring the data close to device. Fog computing has a resource limitation, and also the resources, the computational of the resources is lower than the computational power of cloud computing, but it gives us more advantage, that is the service delay become minimum. So we propose MEHO optimization solution to minimize the service delay by assign the resources to either cloud computing or fog computing. The background and related work, there are many work in fog cloud computing. Some of them use fog task scheduling, and the main objective is to reduce execution time. Other work their aim is to reduce the response time and ensure the quality of service. So for solving the problem, we first give a problem modeling. For the IoT request, it has many characteristics, such as the size of request, the starting time, and the deadlines. For the service delay, we have a delay caused by the transmission time, the waiting time, and the processing time. So the problem is considered as an optimization problem, which is the main target is to minimize the service while ensuring all the deadlines are met in scheduling. So we need an heuristic method or optimization method that can solve complex NP hard problems. So we enhance the elephant optimization algorithm by adding a penalty function to remove invisible solution, and also to enhance the convergence curve or convergence rate of the algorithm. And also the updating of the best individual is done according to the statistical information from candidate solution. So to be able to apply the elephant algorithm, we need to make encoding schema because the MEHO algorithm work on continuous domain, and we need to convert the algorithm to work on discrete domain or binary domain. So the algorithm can obtain the near optimal scheduling for IoT application request. So for the simulation, we use a cloud simulation, and we use a bucket size for each request between 100 and 9,000, and the internal arrival time between requests is about 10 milliseconds, and we compare the proposed algorithm with our algorithm BSO and WFQ. The figure show the comparison between the proposed algorithm and the other algorithm. The first figure shows the service latency versus data size. As the figure shows, the proposed algorithm maintain the minimum service delay across different data size. And also for the missed deadline request, our algorithm achieves the minimum number of missed deadline requests. So our algorithm achieve or answer the research questions. It minimizes the missed number of deadline requests and also minimize the service delay. So conclusion and future work. Our future work is to add cost-effective scheduling. We want to consider the profit of the cloud provider, so we need to maximize the profit for cloud provider, and also we need to apply the algorithm on real world application like 5G problems. Thank you. And any questions?
I have a small question. What is the trade-off to have scheduling to happen on cloud or on Flog? What makes yes?
Yes. Now we have different type of IoT application. Some application has to be processing in real time and doesn't allow any service delay.
Yes.
In this case, this type of request has to be processing in fog computing.
Okay.
For the other requests that doesn't have any constraint on the time and processing time can be processing in cloud computing. So our proposed algorithm make a balance and determine which application or which request has to be assigned in the fog computing and which one has to be moved to cloud computing.
So the decision is dynamically assigned during
Yes, it's dynamically. Yes, it's dynamic.
to scan the traffic of the application.
Yes, right. Yes.
Okay.
Yes.
Okay. Thank you very much.
Okay. Well, thank you.
Okay. Thank you. Thank you very much.
Thank you. Thank you.
Any question?
So, paper 3, titled Enhancing Short-Term Electricity Consumption Forecasting with Deep Learning Models, by Mahmoud Ahmed Mohammed, Nagdi Mahmoud Nagdi, Al-Azhar University, and Karim Amara, Ain Shams University.
Good morning, everyone. Thank you for attending this session. My name is Mahmoud Ahmed, and today I will present our work titled Enhancing Short-Term Electricity Consumption Forecasting with Deep Learning Models. This search was done in collaboration with Dr. Nagdi Mahmoud and Dr. Karim Amara. Here's the outline of my presentation. I will start with a short introduction about the energy challenge, then explain the problem statement and our contribution. Next, I will describe the proposed deep learning models, the pre-processing pipeline, and the evaluation metrics. After that, I will show the forecasting results, the trade-off between performance and cost, and a comparative analysis with previous work. In the final, I will conclude with key findings and future directions. For the energy challenge, the global energy demand is increasing very quickly because of population growth, technology, and economic expansion. To manage this demand, we need accurate short-term electricity forecasting. So the smart meter plays an important role here. The data that can be used for deep learning using AI and smart meter data together allows us to build a better forecasting systems that help improve grid stability and reduce energy waste. For the problem statement and our contribution, the main challenge in short-term load forecasting is the rapid change in consumption and the complex behavior of the users. Many models work well for single-step forecasting, but struggle with multi-step ahead predictions, where error accumulates by time. Our goal is to build a model that provides accurate and stable forecasting up to 3 hours ahead, even during big demands. We compare 3 models, LSTM, GRU, and our proposed autoregressive GRU, which uses teacher forcing to improve multi-step stability. All model used the same input, which are the last 6 half-hour readings to predict the next value. Our main contribution is the ARGRU model. It uses its own previous predictions as input and apply teacher forcing with a half ratio. This helps the model learns how to handle real multi-step forecasting, making it more stable and more accurate. The dataset used for our research, we used the London Smart Meter dataset from 2013. It contains half-hourly electricity consumption readings from UK households over the full year. The key feature we used include the household smart meter ID, the timestamp of each reading, the electricity consumption in kilowatts, and the ACORN category, which represents the household socioeconomic classification. The dataset originally contains 5,566 households with readings every 30 minutes, resulting in millions of consumption entries throughout the year. Before feeding the data into our model, we applied a pre-processing pipeline to clean and prepare the dataset. Here we present the pre-processing pipeline we applied to the data to include, it includes cleaning, filtering, handling missing values, and aligning timestamps to prepare the dataset for modeling. In dataset used in our experiment, we utilized the public London Smart Meter dataset, a widely used benchmark in energy forecasting research. The dataset provides half-hourly electricity consumption readings collected from UK households through 2030. In data cleaning and filtering, we removed households with incomplete data or non-unique consumption behavior. We kept 228 households after filtering. We categorized them into 5 ACORN demographic groups, A, B, C, D, and E. After cleaning and filtering, we retained 228 households grouped into 5 ACORN demographic groups. From these, we selected a balanced subset of 75 households for our modeling experiments. In the next step, we handled missing values using linear interpolation. We aligned timestamps across all households to ensure consistent time series for modeling. Then we transformed the time series data into supervised learning format. Each sample consists of 6 consecutive half-hour readings used as input. Then the model learns to predict the next immediate reading, which is the 7th value. This approach helped the model capture short-term consumption pattern and trends. In data normalization, we applied min-max scaling to all consumptions values. This transformed the data into 0 to 1 range, making features comparable. The scaling step helps speed up model convergence and stabilizes training, especially for GRU-based architectures. To ensure rapid and generalizable results, we used 5-fold cross-validation. Each fold contains 60% training and 20% validation and 20% for testing. In hyperparameters, all models were trained using the Adam optimizer, learning rate 0.001, batch size 256 for 50 epochs. This consistent setups allows for fair comparison between LSTM GRU and AR GRU. For the evaluation metrics, we used 4 main metrics: mean absolute scaled error, where lower values means better accuracy; R score, showing how well the model explain the variance of the data; daily peak mean absolute percentage error, measuring accuracy during high demand periods; off-peak mean absolute percentage error, measuring accuracy during high demand periods. In this slide, we look at the overall accuracy of the 3 models using mean absolute scaled error and R score. We can clearly see that ARGRU gives the best results. It has the lowest mean absolute scaled error, which means it makes the smallest prediction error. And it has the highest R score, which means it fits the real data much better. At the 3 hours prediction, the ARGRU model reduced the error by 67 compared to the LSTMs, and by 9% compared to the standard GRU model. This demonstrates ARGRU's strong performance in multi-step forecasting. This showed the ARGRU is the most accurate and most reliable model, especially when predicting many steps ahead. Here we compare the model during peak and off-peak hours. During peak times, when electricity use is very high, ARGRU performs the best, predicting these important moments, more accurate than GRU and LSTM. This makes it very useful for managing high demands periods. During off-peak times, when consumption is low, GRU is slightly more accurate, but its predicts are less stable because it high variance. ARGRU, however, gives more stable and consistent predictions, even if the error is little higher. For the visualization, here we compare actual consumption with predictions for both GRU and ARGRU. As shown, ARGRU follows the real consumption curve more closely when predicting many steps ahead. Here we can also see that the ARGRU model follows the real consumption curve more closely when using multi-step predictions. As shown, the yellow curve uses 5 previous predicted values and 1 real reading, yet it still delivers good, acceptable performance that remains very close to the real curve. For the trade-off performance versus cost, although ARGRU is the most accurate model, it requires more computational time. Training GRU takes about 39 minutes, while ARGRU takes around 73 minutes. This shows a clear trade-off. Better performance needs higher computational cost. We compare our model with a benchmark LSTM model from the literature by Pervasive. Their LSTM achieved a mean absolute scaled error of 0.98 for 1 hour forecast. Our GRU improved this result to 0.66, and our ARGRU achieved 0.5. To conclude, the ARGRU model achieved the best performance across almost all metrics. It provides accurate and stable forecast up to 3 hours ahead and handle peak periods very well. Its only drawback is higher training time. In the future, we aim to reduce computational cost, include external features like weather and holidays, explore hybrid architectures such as attention and transformers, improve pre-processing and feature engineering. Thank you. Any questions?
Thank you very much.
I have a question. Anyone have a question? Well, I have a question for you. You didn't mention the machines you got the training on. So can you
The machines
elaborate? Yes, the
The-
machine you used for the training the models. Was it one machine or multiple machines? And the machine specs?
It's
As you
my-
already was talking about the training time and the performance.
Yes, I use my own machine. The training was used.
Was it a
I trained using my
multi-core
machine.
machine with the GPU specs and so on, or
I
انت
used
انت كنت بتتكلم على التريننج تايم، كنت بتتكلم على البرفورمانس والانهانسمنتس، فانا كنت حابه اعرف تفاصيل اكتر عن الماشين اللي انت كنت بتستخدمها.
تمام. I used my own PC. I used graphic card.
عن جي بي يو with
Yes.
GPU capabilities.
Yes, 3060 RTX.
كام كور؟
3060 RTX.
اوكي ثانك يو.
Thank you.
So the fourth paper in this session is batched and hybrid homomorphic encryption performance for real-time privacy-preserving machine learning, authored by ولاء سعد محمود, محمد عبد المجيد سالم, Faculty of Media Engineering and Technology, German University in Cairo, عبد الرحمن حيدر, Department of Computer Science, Faculty of Computer and Information Science, IOT University. Stage yours, only 10 minutes.
The vision for modern healthcare involves continuous monitoring from wearable devices like smartwatches and ECG bands to provide real-time diagnostic and to protect sensitive patients' data. We use technologies like homomorphic encryption, which allows computation directly over encrypted data. However, there is a major problem on resource-constrained devices where traditional homomorphic encryption is prohibitively slow. The latency scales linearly with the amount of data, making continuous real-time processing practically impossible. Our goal is to bridge this gap to enable efficient, accurate, and private inference on the edge. To tackle this challenge, I will first introduce our solution and optimized architecture using patched homomorphic encryption. Then I'll walk you through our comprehensive performance evaluation, looking at both computation and communication costs. Finally, I will discuss the impact on model accuracy and conclude with the key takeaways from our work. The core of our contribution is a shift from a naive sequential approach to an optimized patched one. In the naive method, every single data sample is encrypted individually. This is inefficient because the cost grows directly with the number of samples of order n complexity. To mitigate this overhead, existing solutions employ hybrid homomorphic encryption. As illustrated here, the hybrid homomorphic encryption optimizes the client-side workflow by encrypting the data using efficient symmetric encryption, while only the secret key is encrypted using the homomorphic encryption. This architecture offloads the heavy computational burdens to the server side, specifically during the homomorphic decryption phase, thereby reducing the initial encryption load compared to the naive baseline. However, while hybrid homomorphic encryption improves upon the naive approach by reducing client-side computation, it doesn't fully resolve the throughput scalability issue inherent in processing individual data streams. This is where the hybrid homomorphic encryption improves upon the naive approach by reducing client-side computation. It doesn't fully resolve the throughput scalability issue inherent, sorry. This is where our dynamic patched homomorphic encryption proves superior to both, unlike the sequential nature of the naive homomorphic encryption or the single stream focus of the standard hybrid homomorphic encryption. The question is, how do we escape the one at a time bottleneck of naive and hybrid homomorphic encryptions? Our answer is in dynamic patching. Instead of encrypting single samples, the naive slot packing, we pack over 100 samples and up to 128 into a single ciphertext of the PFV and CKKS schemes. This fundamental restructuring slashes the complexity from a linear of order n down to order of n by 128, which doesn't just reduce the computational load, it fundamentally changes the performance. The cost is no longer tied to the number of individual samples, but to the number of patches, giving us efficient throughput and near constant latency needed for practical privacy-preserving machine learning. Our evaluation is based on a standard three-party model for privacy-preserving machine learning. We have the client, a patient with a wearable sensor, who encrypts their sensitive data. This encrypted data is sent to a powerful but untrusted server, which hosts the machine learning model and performs the heavy computations. The server is honest but curious, meaning it follows the protocol but might try to learn from the data. Finally, the analyst or the model owner receives the encrypted results, which only they can decrypt. Our work focuses on optimizing the client-side operations to remove the performance bottleneck. To benchmark this framework, we utilized the MIT BIH arrhythmia database. We processed 128 feature ECG samples to perform a binary classification task distinguishing between healthy and unhealthy heartbeats. We evaluated using two schemes, the PFV, where data is quantized to 4-bit integer for exact arithmetic, and the CKKS, which handles approximate floating point numbers. We then compared our approach against three distinct baselines: the naive unpatched method, and the hybrid homomorphic encryption with PASTA protocol, and the pure symmetric encryption as a control. So what does this optimization look like in practice? This graph shows the client-side encryption latency on a logarithmic scale. The top line represents the hybrid homomorphic approach from the benchmark, which still scales with the input size. For the 2000 data input, it takes nearly 5 seconds. Here in the table. Now look at the bottom two flat lines. Those are our patched PFV and CKKS schemes. Those are our patched the bottom lines. The encryption time remains nearly constant, under 15 milliseconds, regardless of the number of inputs compared to a naive sequential implementation. This is a speed up of over 330 times for the CKKS and 540 times for the PFV. This is the difference between a system that's theoretically possible and one that's practically deployable. Beyond computation, communication overhead is a major concern for the edge devices. This graph compares the size of the upload ciphertext. As a baseline, we show standard symmetric encryption at the bottom. While it offers the lowest constant overhead, it doesn't support computation on the data. In comparison, the traditional hybrid homomorphic encryption approach, like the PASTA, allow for computation but scale linearly, meaning more data results in a significant larger payload. In contrast, our patched PFV and CKKS schemes maintain a constant communication profile similar in behavior to the CKE or the symmetric encryption baseline because the ciphertext size is fixed by the cryptographic parameters. The transmission cost remains the same whether we process a single sample or fill the entire patch capacity. The predictability is crucial for streaming applications as it effectively decouples the bandwidth requirements from the data volume, ensuring stable network performance. Looking at the full end-to-end pipeline, we see a clear winner for latency-sensitive workloads while client-side encryption times are comparable. The CKKS significantly outperforms the PFV in both server-side evaluation and analyst-side decryption. So the first row in the table is for the client-side encryption, the second row is for the server evaluation, and the third for the analyst decryption. However, the PFV remains a crucial alternative for applications that require the formal correctness guarantees of exact integer arithmetic. The most important question is, does the massive speed up come at the cost of accuracy? The answer is definitive no. We validated our framework on the real-world MIT PIH arrhythmia dataset as shown in this table. Our encrypted inference models using both PFV and CKKS consistently achieve accuracy up to 100% on smaller patches and maintain over 97% on larger ones. Crucially, our encrypted models often surpass the accuracy of the non-encrypted plain text benchmark. This shows that we can achieve strong privacy and high performance without compromising model fidelity. In conclusion, we have presented a practical and optimized architecture for real-time privacy-preserving machine learning on edge devices. Our key contributions. First, we demonstrated
We have 2 minutes, 2 more minutes.
Orders of magnitude performance gains of over 300 times by using a patched homomorphic encryption approach instead of the naive method. Second, we showed that this approach leads to a constant communication cost, making it ideal for continuous data stream. And finally, we achieved all of this while maintaining high inference accuracy, reaching up to 100% on encrypted biomedical data. The broader impact of this work is practical blueprint for deploying GDPR and HIPAA compliant secure computing solutions to sensitive fields like healthcare, helping to move these powerful privacy technologies from theory to practice. The future work looking ahead, we have several exciting directions for this research. We plan to extend this framework to more complex multi-layer neural architectures and explore hardware acceleration on FPGAs. To further boost performance, we are also interested in investigating hybrids with multi-party computation and applying our method to higher dimensional data like medical imaging. Thank you.
Thank you very much. Any questions? So I have a question. You mentioned that about the accuracy, that you still the accuracy is valid up to 100%. Can you give us insight about what kind of arithmetic operations or data operation performed on the encrypted data, and how did you achieve the 100% accuracy compared to the normal plain text operation? Did you meet your experiments about a specific domain, like images, or what kind of application?
Heartbeat, the ECG.
Can you use mic, please?
Oh, sorry. The ECG, heartbeats.
ECG. So what kind of operation you made on ECG?
What kind? We applied addition of matrices and dot product.
Okay. And this kind of operation is enough for normal IoT or a healthcare operation?
Yes, as far as I read in the previous articles and related work,
Okay.
they were applying one operation, and we had also the benchmark to compare with the hybrid homomorphic encryption.
Okay.
So they applied one operation, and we applied also the dot product to enhance the work.
Okay. Okay. Thank you. Any more questions? Okay. Thank you very much, Dr. Wale. So, حاضر عينيا. So we have the fifth paper is developing graph-based models for mobile network management in IoT, authored by Amr Adel Abdel Wahab, Information Technology Department, Asyut International Technological University, Muhammad Abdul Rahman, Electrical Engineering and Computer Science Department, Juster Institute of Technology Dubai, Mamdouh Farouk, Computer Science Department, Asyut University, Abdurrahman Haider, Computer Science Department, Asyut University. The stage is yours. Thanks.
My name is Amr Adel Kamal, and I'm leading development graph with model for mobile network management in IoT. This is our available table content, introduction, then problem definition, research gap, research objective, proposed hybrid DE VNS, our hybrid algorithm, workflow and fitness function, experiential setup and result and conclusion. First, introduction. طيب بص مش بحب اقرا السلايد، ممكن اتكلم تمام. احنا عندنا مشكله في الاي او تي في الموبيليتي بين الاجهزه بتاعت الشبكات واجهزه النتورك. ازاي؟ احنا عندنا شبكه من الاجهزه مختلفه، الاجهزه المختلفه دي ازاي نوصلها ببعض من غير ما يبقى في حاجه سنترلايزد تقدر ان هي توصل لهم انترنت، دي اللي بنسميها الموبايل اد هوك. خلاص؟ فاحنا ازاي نقدر نوصل الاجهزه دي ببعض، وازاي نقدر يبقى في كفر والاجهزه دي تقدر ان هي تتعامل وتوصل ببعض. فدي مشكله، لان الجهاز اللي في جيبي مش زي الجهاز اللي معاك، مش زي الجهاز اللي بيستخدمه اي حد تاني قاعد في مكان تاني. فاحنا عندنا ان التوبولوجي بتاعتنا مش ثابته، لان في موبيليتي كتيره. الانرجي بتاعت الموبايلز او الهوستس او الاجهزه او النودز، تعالى نتكلم ان هي نودز مش زي بعض. فاحنا محتاجين ان احنا نعمل تغطيه كبيره ونعمل ازاي نقدر نخلي النتورك واصله بين الاجهزه دي كلها وبين بعض. طيب، فالمشكله اللي بتبقى عندنا احنا عشان نمثل الطريقه دي بنستخدم الجراف ثيوري. ليه الجراف ثيوري؟ الجراف ثيوري عشان نقدر يساعدنا ان احنا نمثل الشبكه دي رياضيا. يعني احنا لو حبينا ان احنا نرسم او حبينا ان احنا نتعامل مع الاجهزه مش هنقدر، فلازم نمثلها رياضيا بباينري سيستم عشان نقدر ان احنا نحل مشاكلها ونشوف مشاكلها، ونقدر ان احنا نمثلها على الالجوريزم نتتبع خطواتها عشان نحل المشكله بتاعتنا. طيب، البروبلم ديفينيشن. ايه المشكله في ان الاجهزه توصل ببعض؟ احنا هنا عندنا حاجه اسمها مينيمم دومينينج سيت، يعني احنا محتاجين نجيب اقل عدد من الهوست، او تعالوا نسميها النودز، اقل عدد من النودز اللي هي تقدر ان هي تغطي الاجهزه ان هي تتواصل مع بعض، اللي بنسميها الكفرج. والمشكله دي بنسميها ان بي هارت بروبلم. ليه ان بي هارت بروبلم؟ لان صعب جدا ان يبقى في احتمالات كتير. احنا مثلا لو الاجهزه او النتورك بتاعتنا كبيره، ففي عدد، احنا لو بنمثل باينري فبنمثله ب2 اس ان، فاحتماليات ان الحاجه دي توصل او انت توصلها لحل بيرفكت يعني بيبقى صعب. فدي بنسميها ان بي بروبلم. عشان كده بنحاول ان احنا نطلع الجوريزمز. الاجتهادات طلعت ان احنا نعمل هايبرد الجوريزم عشان نقدر نحل المشاكل دي. تمام؟ فالهدف بتاعنا دلوقتي ان احنا نطلع اقل مينيمم دومينيتنج سيت. طيب، ايه المشاكل في الريسيرش جاب بتاعتنا؟ ان اغلب الابحاث بتركز على حاجه واحده، على مشكله واحده، يا اما الكفر يا اما الانرجي. وبعض الابحاث اللي استخدمت الهايبرد ما قدرتش ان هي تعمل ادابتيف او بالانس ما بين الاثنين. تمام؟ فاحنا بنحاول ان احنا نطور حل لوكال سيرش وجلوبال سيرش من خلال نموذج او الجوريزم هايبرد ما بين اللوكال والجلوبال. ازاي ده بيتم؟ فاحنا الاوبجيكتيف بتاعنا ان احنا نطلع حل بسيط. تعالى نمثله بمثال. يعني احنا مثلا طالعين كامبين مخيم، اتقسمنا لمجموعات، دي النتورك بتاعتنا، فاحنا محتاجين 1 و2 و3 أو 4 اشخاص هم المسؤولين في كل جروب، ان احنا نقدر نتواصل معاهم عشان نقدر نعمل كفر، او نقدر ان احنا نخلي الكامبين بتاعنا كامل او متواصل مع بعضه. طيب تعالى نقول ان في واحد عي او وقع، هنعمل ايه؟ لازم يبقى عندنا فولت توليرنس، عندنا حل بديل سريع، عندنا ان احنا نقدر نطلع نودز او نقدر نطلع واحد جديد يقدر ان هو يقرب المجموعه دي. فاحنا بنقسم الحلول بتاعتنا هنا لحلين، حل اسمه جلوبال سيرش وحل اسمه لوكال سيرش. الجلوبال سيرش بتاعنا بيبدا يعمل ايه؟ الجلوبال سيرش بتاعنا بيبدا ان هو يشوف مين اللي هيمثل كل مجموعه، يدور من بره، يتحرك في كل منطقه. عندنا شكل النتورك وهي مرسومه، هنبدا نتحرك يمين وشمال فوق وتحت عشان نقدر نطلع احسن واحد او احسن حل يقدر يغطي اكبر مجموعه من النودز او اكبر مجموعه من الاجهزه اللي عندي او اكبر مجموعه من الاشخاص. تمام؟ فالنتورك بتاعتنا كده من بره بقت خلاص متوصله. طبعا بعد كده بنبدا ان احنا نحسن ازاي بقى، ده اللي احنا اقترحناه، ان احنا هندمج ما بين جلوبال سيرش بالديفرنشال ايفوليوشن وما بين اللوكال سيرش عن طريق الفاريبل نيبرهود سيرش. احنا بعد ما طلعنا الحل ده هنحاول نعمل له سواب، هنحاول نلغيه، هنحاول نوصل واحد جديد عشان نقدر ان احنا نوصل لاحسن حلول ممكنه وتبقى النتورك دايما فيه كفرج ونقلل فقدان الانرجي بتاعتنا. طيب ازاي ده احنا بنتم؟ احنا بنعمل هنا انيشال بوبيوليشن، والانيشال بوبيوليشن بتاعنا دايما بيبقى راندوم. ليه؟ عشان ما نقعش في مشكله الاوبتيمال. يعني مثلا عايز اقول لك في اللوكال اوبتيما معناها احنا مثلا لو قاعدين في صحراء فعايزين نشوف اعلى نقطه، فوصلنا لتل، على مستوى نظرنا ان احنا خلاص احنا وصلنا للهدف والتارجت بتاعنا دي اعلى نقطه، بس احنا مش شايفين الجبل البعيد اللي هو فيه اعلى منه او الحل الامثل. عشان كده احنا بنشتغل راندوم، لان احنا لو بدانا بحل ثابت ممكن يكون ده الحل السيء، فلا احنا محتاجين حلول كتير، نجرب على الحلول اكتر وهكذا. تمام. بعد كده هنرن الديفرنشال ايفوليوشن بتاعنا عن طريق الميوتيشن والكروس اوفر عشان نقدر نتحرك في كذا اتجاه ونقدر ان احنا نطلع افضل حل، والحل ده نربطه بحلول جايه، والحل القديم يتربط بالحل الجديد وهكذا. وبعد ما طلعنا افضل حل هنحاول ان احنا نحسنه كمان عن طريق اللوكال سيرش بالفاريبل نيبرهود سيرش، ان احنا نبدل او نضيف او نلغي بعض النودز ونشوف هل ده بيحقق اقل كفر عندي او اقل مينيمم دومينيتنج سيت اللي يقدر هو يغطي الشبكه كلها ولا لا. ده الالجوريزم بتاعنا. الفتنس فانكشن. طيب الفتنس فانكشن دي عباره عن ايه؟ دي اللي هي بتحسن الحلول او بتقول ان الحل بتاعي كويس ولا لا. احنا هنا ربطنا الفتنس فانكشن بتاعتنا بشويه حاجات زي الكفرج والانرجي افشنسي والمينيمم سايز او مينيمم دومينيتنج سيت سايز، لان احنا عايزين نوصل لاعلى تغطيه واقل فقدان في الطاقه واقل عدد من النودز اللي هي تقدر تعمل كفر للنتورك بتاعتي. طيب الاكسبيرمنتال سيت اب استخدمنا ماتلاب R2 او 2023 بي، ويا دكتور حضرتك احنا استخدمنا RTX 4090 في الاجهزه بتاعت الاي اي اللي جايه في الجامعه، انا استغلتها الصراحه. وقارنا ما بين بعض الالجوريزم الموجوده في الهايبرد اللي استغلت الهايبرد عشان نشوف هل احنا حققنا الكفرج او حققنا اقل مينيمم دومينيتنج سيت ولا لا. فالريزلت بتاعنا من ناحيه الكونفرجنس، من ناحيه التقارب، هنلاقي ان هو كان سموث جدا من اي جنريشن احنا عملناه واقل مينيمم دومينيتنج سايت، وده معناه ان الالجوريزم بتاعنا بيوازن كويس ما بين الاكسبلويتيشن وما بين اللوكال بتاعنا. طيب بعد كده لو شفنا برضو المقارنات ما بين الدومينيتنج سايت سايز في البنش مارك بتاعنا، هنلاقي ان هو حقق اغلب الدومينيتنج سيت، وخصوصا في النتورك الكبيره. احنا هنا ممكن نكون وصلنا ل 1000 او 200 نودز في النتورك بتاعتنا اللي جربنا فيها، وده بيقول ان في سكابيليتي وفي افشنسي يقدر يقدمها الموديل او الالجوريزم بتاعنا. لو بصينا برضه على الاستابيليتي اناليسيس والفرق ما بين افضل حل ومتوسط النتائج او الافريج، هنلاقي ان الفرق قليل، وده بيدل ان الالجوريزم بتاعنا برضه قدر ان هو يحقق الكفرنج كويسه ويدي حلول كويسه وما يقعش في مشكله اللوكال اوبتيما. الكونكلوجن باختصار، بعد ما شرحنا الفكره وشرحنا الالجوريزم بتاعنا وان هو دمج ما بين تو الجوريزم الديفرنشال ايفوليوشن والفي ان اس، فالالجوريزم الهايبرد بتاعنا اللي احنا سميناه دي اي في ان اس قدر انه يحقق اصغر مينيمم دومينيتنج سيت، يعلي او يحقق التغطيه للشبكه بتاعتنا، يقلل استخدام الطاقه، ويحقق كونفرجنز بثبات عالي. الفيوتشر ورك احنا هنستغل ده بقى في الموبيليتي في النتورك الكبيره، وعايزين نستخدمه في الاي او تي تيست بيدز، وكمان ان شاء الله في الجي بي اس هنحاول على قد ما نقدر. شكرا.
شكرا جزيلا.
عيوب السيستم ان احنا عشان نحقق الحاجه اللي احنا وصلنا لها دي، انا اضطريت ان انا يعني محتاج اجهزه عاليه بامكانيات مواصفات عاليه جدا، وده ما كانش متحقق في الاول. السوليوشن ما كانتش متحققه بده اصلا غير من فتره قريبه قبل ما ننشر، لدرجه ان احنا طلبنا من الجامعه يعني ان هي توفر لنا حاجه زي كده من الاجهزه ان احنا نقدر نشتغل عليها، عشان الالجوريزم بتاعنا ما بيقدرش ان هو يتعامل مع النتورك الكبيره بسهوله.
بس انا قصدي لو فرضنا خلاص انت خلصت تجربتك واخدنا السوليوشن ده نطبقه دلوقتي، هيظهر ليه حاجات بقى يعني دروباكس او تخلي السوليوشن ده مش احسن حاجه. فعندك ايه الجوانب النقص فيها؟ يعني مثلا هل انت قست الباندويتس اوفر هيد اللي على النتورك؟ هي هتبقى نتورك نوعها واي فاي ولا حاجه تانية؟
لا احنا اشتغلنا على الاد هوك والوايرلس سنسور نتورك، ما اشتغلناش
اد هوك. طيب هل هي هيبقى في باندويتس اوفر هيد كبير مثلا؟ جوانب السلبيه في تطبيق اي سوليوشن يعني.
مش فاهم قصد حضرتك من ناحيه
يعني ايه امتى السوليوشن ده يبقى مش احسن حاجه؟
امتى الايه؟
امتى السوليوشن ده السيستم اللي انت قدمته ده امتى ما يبقاش احسن حل للسيستم بتاعنا؟
ما عشان كده احنا حاطين داله البنالتي. لو داله البنالتي احنا حاطينها في الالجوريزم بتاعنا، لو اديتنا قيمه كبيره ما بنقدرش ان احنا نقول ان ده بيست سوليوشن بالنسبه لنا. ده لو انا فاهم قصد حضرتك. يعني انت قصد حضرتك ان انا لو طبقت الابلكيشن بتاعي او الالجوريزم بتاعي ايه الحاجات اللي هو ممكن ما يحققهاش؟ فاحنا لو زادت عدد النتورك بس.
يعني
احنا
هو
جربنا
مش
في البنش مارك
يعني.
بتاعتنا كانت عند 700 ل 800 جهاز او 700 800 نود.
تمام. يعني هو الليميت بتاعه يعني 700 800 نود، يعني هو مش
بالظبط.
سكيلبل اكتر من كده. شكرا.
ما عاديش عن كده.
Any more questions? Okay, thank you very much. So the next paper is the evolution of metaverse for smart psychotherapy system, authored by Ahmed Abed, Faculty of Computer Information Sciences in Shams University, Tamer Abdel Qadir, Faculty of Computer Science and Engineering, Jalal University, Mohammed Hashim, Faculty of Computer and Information Sciences in Shams University, presented by Ahmed Zidan. presented by Dr. Tamer.
So let me introduce the first author, Ahmed Zidan Abed. He was a PhD student. He finished his PhD under supervision of Dr. Mohammed Hashim and myself. And this is one of his last papers. It is about applying the cyber physical social systems to psychotherapy system. So his PhD is mainly about cyber physical social systems, which is has a main application in metaverse. Metaverse is a virtual world which combines physical systems like sensors, cyber systems like computers and networks, and social systems which are the humans using these systems. So metaverse is a good application for a cyber physical social system. So he, Ahmed, the first author, he was trying to prove that this application could fit into a psychotherapy system well. So he first introduces the cyber physical social system. As we said, it is a combination of three elements, three components: the physical, which are the sensors; the cyber, which are the networks and computers; and the social, which are the human interacting with these components. And in the middle of these three components is the CPSS, or cyber physical social system. The related work, there are some applications that have targeted this combination of the three components, including those in the medical field. And in the industrial field, Internet of Things, healthcare, transportation. All of them uses the three components: sensors, computers, networks, and humans interacting with each other. Traditionally, there was a cyber physical only, so the social component was introduced later. These are all applications. The characteristics of the cyber physical social system is that the interaction of the human facilitated the human oriented services, so can give services much better than the traditional cyber physical only systems. The metaverse is a perfect application for this three component architecture, which again, it is composed of physical components that are the glasses which you can put on your eyes to enter the virtual world of the metaverse, and could include later sensors in your hands, in your legs. The second, which is a computer which processes the data, and the networks to connect the human wearing these sensors to the cloud server, and the third, which is the human using this system. Okay, that is a diagram showing the interconnection between the three components. In terms of the psychotherapist, we have the human who is the patient talking with the doctor who is a psychiatrist through sensors like the glasses the patient is wearing, and could also include some wearable devices on hands, on legs, on some of the body parts through computers and networks. This is the cyber system. Okay, so what is the benefit of modeling this system as a cyber physical social system? The benefits could include targeting the standards of cyber physical social systems. So this architecture has gained attention in the last years and has some proposed standards, and in addition, the challenges in implementing such a system. So when we classify or when we describe a system and prove that this system applies to this architecture, then we can use the standards, we can tackle the challenges. And in this paper, we present some of the security challenges included in this architecture. So the first slide includes 3 of them. Bad mouthing. Of course, we have in the metaverse, we can have many nodes in this virtual world, not just the patient and the doctor. This could include other humans, and every human has his sensors, and we have other computers connected to the system. So maybe some of these nodes in the system could talk badly about the others, could give bad reputation. We have the ballot stuffing attacks, when a malicious node offers favorable recommendations. So you can see that a review about a doctor who is not good but has a false reputation to be good while he is not good, that is ballot stuffing. So it can be a community that recommends false recommendations. Self-promoting attacks, when a malicious node offers favorable recommendations about itself. Opportunistic service attacks, when a malicious node offers quality service to establish a high degree of trust. Then, after it gains the trust of the community, it switches to its malicious behavior. On-off attacks, when a node switches between the good behavior and the bad behavior, so that it is not described as a malicious node, while it is a malicious node. The node capture attack, it is someone who can capture the node itself, can take the place of a patient or of a doctor and act as if he is the owner of this device. Injection attacks when a malicious code is introduced into the system. Sybil attack when a node identifies itself by multiple identities. Of course, it should have one identity, but it deceives the others by identifying itself with multiple identities. Denial of service, of course, it is the attack on a server through a huge number of data so that the server cannot continue offering the service. Spoofing attacks when someone takes the identity of another one. Black hole attack when the data comes to some node and this node absorbs the data so it does not propagate in the network. And the other one, the wormhole attack, when a node bypasses data to some other node, so they can be two malicious nodes agreeing with each other to bypass the data. So these are some of the security challenges that has been encountered to target this kind of architecture, especially when it is applied to the medical or healthcare services. The first 5 is about the trust issues. The next 2 is an application attacks, and the last 5 is a network attacks. So in conclusion, cyber physical social systems are applied to many applications, including the healthcare applications, and this one is a psychiatrist communicating with a patient. And as we have seen that applying this architecture provides a way to standardize the protocols used, the technologies used, and to tackle the challenges faced by this architecture. Thank you.
Okay, so the work will be, any questions here from the audience? Okay. So the work will be in the next papers, evaluation and...
No, actually we have already some papers about authentication, about trust issues. So we already solved these attacks, some of these attacks, not all of them,
Okay.
in some other papers. So yeah,
Okay.
but I mean, we are presenting the work that has some future work that we already have done.
Okay.
Yes.
Okay, thank you very much.
Thank you.
Thank you. So the last paper is a study of brain image segmentation techniques, bridging classical methods and quantum innovations.
Assalamu alaikum. My name is Salma Mustafa, assistant lecturer in Ain Shams University, with the collaborate of Dr. Sal Sabir and Professor Abir and Professor Said. We manage our paper in quantum technique by using or design a bridge between classical and quantum innovation according to brain image segmentation. First, central nervous system is a complex frontier which composes of brain and spinal cord, which is responsible for sensory and monitoring function, and the architecture of brain is cerebellum and brainstem. Cerebellum is manage or monitor controlling and coordination. And brainstem connect between spinal cord and cerebellum. Cerebellum is innovative in high connected process like judgment and problem solving. Critical challenge is brain tumors and ischemic stroke, which is سكتة يعني زي السكتة الدماغية. Precise image techniques, which is practically MRI, are essential for diagnosis of brain tumor and smash strokes. Okay. لا مش عشان نفسي بس. Brain tumor has grades from 1 to 4, which 1 is slow growing and 4 is high aggressive and rapid speed, which is varied between shape, location, size, and intensity, which smash stroke is distributed of blood flow to the brain and required to prompt recognition for effective treatment. Evolution of segmentation methodology from traditional activity control modeling to cutting-edge quantum machine learning. First is traditional method, then deep learning, then quantum innovation, which traditional methods of active control modeling, deep learning, convolution neural network, CNN, then quantum innovations, which is hyper quantum classical frameworks as integration. First, classical segmentation has variations such as active control modeling, fuzzy clustering, atlas-based methods. Active control modeling, these methods have advanced over device similarity coefficients range between 85% to 96% in various studies. First, active control modeling is minimize energy functions to eliminate tumor boundaries. Fuzzy clustering is enhanced segmentation in the percent of noise, weak boundaries. Atlas-based method use predefined anatomic template to guide segmentation and improve consistency. Quantum innovation by the usage of quantum machine learning is revolution medical imaging with its potential for superior accuracy, efficiency, and protective power. First, such as quantum CNN, which these techniques achieve accuracy up to 99.67%. Quantum CNN, which transform features into high-dimensional quantum states. Hyper framework combine quantum CNN with convolutional deep CNN. Its integration between them. Quantum enables signification, reduce execution time for the complex optimization problem. Key breakthrough in quantum enhanced segmentation in the recent study, which is Redmark achieved in the brain tumor detection. First, IDLAQET, which is referred to integration of deep learning quantum entropy techniques for brain tumor age detective and classification model, which is mean of that. Achieve high accuracy in brain tumor and detect the boundary and detection. Higher percentage of quantum CNN, which outside accuracy in the classifying of brain tumors for MRI images. While evaluation QU in SBIRD used in 3D MRI image or brain tumor segmentation, which is challenge in the quantum methodology of usage of quantum methodology, like high cost of equipment, hardware, infrastructure, and qubit instability, and limit in qubit count, which led to a scale or struggle for the scale of large clinical imaging data sets. Future direction for the quantum models. First, model optimization, technology integration, and precision medicine. While this focus on scaling and generalize and integration of the quantum image technique to enhance clinical applicability, Then conclusion is the integration of the quantum computing in the medical imaging over a transformative path, revolution brain tumor management to improve patient outcome through enhanced accuracy and increase efficiency and personalized treatment and clinical adaptability. These some of the reference uses. Thank you. Any questions?
Thank you very much. Any questions? Okay, then we have a certificate for you.